6,428 pounds per square inch. The pressure inside one cylinder of a top fuel engine at the moment of combustion. Not internal combustion in any conventional sense. A controlled detonation, repeating 8,000 times per minute, burning 15 gallons of nitromethane in a single quarter-mile pass. Now multiply that by 6. The 6-engine Dragster was never built to win a championship. It was built to answer one question nobody in drag racing had thought to ask. What happens when aerospace engineers with an unlimited budget apply everything they know to the single problem of going as fast as physics allows? What happens was simultaneously magnificent and catastrophic. The car produced elapsed times the sport wouldn't officially match for 15 years, burned itself to scrap on a private airstrip, and rewrote the NHRA rulebook without making a single sanctioned pass. The timing slips say 5.39 seconds. The record books say nothing. To understand where the 6-engine Dragster came from, you have to understand the particular cultural moment that produced it. The early 1960s in Southern California, when the Apollo program was simultaneously drawing the most talented engineers in the country into aerospace work and creating, as a byproduct, a generation of technically sophisticated young men who had been trained to solve previously impossible problems and weren't entirely certain what to do with that training on weekends. The region was saturated with them. Lockheed's Skunk Works in Burbank, North American Aviation in Downey, where the Apollo Command Module was being designed, JPL in Pasadena, Hughes Aircraft in Culver City. Within a 2-hour drive of Lions Associated Drag Strip in Long Beach, Fontana Drag City, and Fremont Dragway up in the Bay Area, there were perhaps 60,000 aerospace engineers, people who spent their working hours calculating stress distributions in aluminum alloys, optimizing combustion sequences in rocket motors, and modeling heat transfer in re-entry vehicle heat shields. On Friday nights, many of them went to the races. Most of them watched. A handful started asking questions the regular hot rodders weren't asking. The man who became the driving force behind the 6-engine project, known within the racing community simply as Doc, his legal name, kept deliberately out of the published record for professional reasons that will become clear, was a senior structural analyst at a defense contractor holding significant subcontracts on classified aerospace programs. His specialty was failure analysis, understanding why structures failed under stress, and engineering systems capable of absorbing forces beyond their theoretical tolerance without catastrophic breakdown. He had been attending races at Lions since 1958. He understood what nitromethane was doing inside a top fuel engine better than most of the people actually running those engines, because he could work through the thermodynamic calculations from first principles rather than relying on empirical rules of thumb that had evolved through trial and error in the pits. What bothered him professionally was the waste. A single top fuel engine of the era, a blown and injected 392 Chrysler Hemi running on 90% nitro, was producing somewhere between 2,000 and 2,500 horsepower at the crankshaft. Of that power, perhaps 60 to 70% was reaching the rear wheels, the rest absorbed by drivetrain friction, flex, and supercharger parasitic drag. What remained was being put to ground through 2 rear tires, each roughly 9 inches wide, on a burnout-prepped asphalt surface. The traction limit was the binding constraint, not a combustion limit, not a mechanical limit, a friction limit. The fundamental physical ceiling imposed by the coefficient of static friction between rubber and road surface, which for the tire compounds and strip conditions of 1963 sat somewhere around 1.1 to 1.3 g of longitudinal acceleration. Doc calculated that a single top fuel engine was already producing more power than a 2-tire dragster could effectively use. The solution to him was obvious. use multiple driven axles. More tires in contact with the strip meant a larger combined contact patch. A larger contact patch meant the physical system could absorb more total power before traction failed. The math scaled linearly. The engineering, as he was about to discover, did not. Construction began in early 1964 in a rented space at a general aviation airport in the San Fernando Valley. A corrugated steel building that smelled of avgas and two-part lacquer, large enough for a small aircraft and barely large enough for what Doc and his 3 investing partners had in mind. The chassis took 8 months. It was fabricated from 6061-T6 aluminum alloy using aircraft construction methodology. TIG welded rather than MIG welded, with every joint subjected to dye-penetrant inspection before the next component was attached. The engines themselves served as structural members, reducing the mass that would otherwise have been required for a frame strong enough to resist the torsional forces of 6 engines firing in coordinated sequence. The overall dimensions, 286 inches in length, with a 230-inch wheelbase between the front axle and the rearmost driven axle. The longest purpose-built dragster constructed to that point in history. The 6 engines were Chrysler 392 cubic-inch Hemis. Doc chose the Hemi for its power-to-weight ratio, its extensive aftermarket support, and crucially, because he had access to detailed Chrysler factory engineering documentation through professional channels. All 6 were blueprinted to identical specifications by a single engine builder who worked on nothing else for the better part of a year. Identical compression ratios, identical valve timing, identical port volumes, measured to tolerances that the racing community of the era was not accustomed to demanding. Each received a GMC 671 Roots-type supercharger and Hilborn port injection. Each was modified for 90% nitromethane compatibility. Enlarged fuel passages, revised valve seat angles, combustion chamber geometry tuned to the different detonation characteristics of nitro versus gasoline. Doc's calculations suggested each engine would produce between 1,800 and 2,200 horsepower. 6 engines, somewhere between 10,800 and 13,200 horsepower at the crankshafts. At the wheels, accounting for drivetrain losses and the mechanical synchronization overhead, the practical number was closer to what the project's informal documentation described as 18,000 horsepower, a figure that was part engineering estimate and part deliberate provocation, chosen because it was large enough to communicate the magnitude of the undertaking to anyone who encountered it. The 3 driven axles were arranged in a tandem configuration. The forward pair of engines drove the middle axle through a common jackshaft. The rear pair drove the rearmost axle directly. A single engine driving the front of the 3 driven axles provided independent thrust. The synchronization system, the most technically original component of the entire project, was a central timing gear train, driven off the number 1 engine's crankshaft, with vernier adjustment capability for each of the 5 secondary engines, capable in theory of holding all 6 within 2 degrees of timing alignment at any RPM. The fuel delivery system was designed around aircraft-grade pumping components. 6 engines running at peak demand required approximately 42 gallons of nitromethane mixture per minute, more than most drag strips could manage through their entire pit delivery infrastructure. Individual pressure regulators prevented a failure in one fuel circuit from cascading into the others. The exhaust management problem was addressed with ceramic thermal barriers and heat-resistant alloys sourced through Doc's aerospace connections. Materials that were, strictly speaking, controlled military specifications components, which is one of several reasons his name was kept out of the project's public documentation. Fully fueled and with driver aboard, approximately 3,800 pounds. A competitive top fuel dragster of 1966 weighed roughly 1,500 pounds. The six-engine car was more than twice as heavy as its theoretical competition. Doc had accounted for this in his calculations. What his calculations did not fully account for was the dynamic weight transfer problem that would nearly end the project before it produced a single clean pass. Run number 1 took place on a Thursday morning in March of 1966 at a private airstrip east of Los Angeles. Roughly 1,200 feet of concrete runway, surrounded by desert and nothing else, which is exactly what you want when you are doing something that nobody can be entirely certain won't produce a fireball visible from cruising altitude. It did not produce a fireball. The startup sequence required 11 minutes. Each engine was individually primed, started on gasoline, brought to operating temperature, then transitioned to the nitro mixture in a specific sequence designed to avoid overloading the synchronization gear. Train before all 6 were running in phase. The sound of 6 blown nitro engines idling simultaneously was described by the machinist who served as crew chief, a man from Glendale who had never worked in aerospace and whose instincts about mechanical reasonableness had already proven more reliable than several of the engineering calculations, as the inside of a turbine test cell, but somehow angrier. When Doc staged the car and brought the engine package to launch RPM, the combined fuel pressure in the system was approximately 750 pounds per square inch. The 6 superchargers were spinning at roughly 16,000 revolutions per minute each. The 6 rear tires, custom-made 10.5-inch compounds, the widest available, pressed onto the concrete with a combined normal force of approximately 3,200 pounds. The run lasted 1.8 seconds before Doc lifted. What happened in those 1.8 seconds is preserved in handwritten notes. The car accelerated with a violence that exceeded the most optimistic prior calculations. The front wheels lifted approximately 30 feet from the start, not the controlled wheel stand of a tuned top fuel car, but an abrupt rotation arrested only by the weight of the forward engine bank pulling the nose back. All 6 tires broke loose simultaneously at roughly 1.2 seconds, at which point the car had traveled perhaps 200 feet and was moving somewhere between 90 and 110 miles per hour, according to the hastily positioned timing equipment. Doc lifted. The mechanical shock of cutting throttle on 6 nitro engines simultaneously cracked 3 exhaust header primaries. The car coasted to rest 600 feet from the start. Nobody was hurt. The car was damaged, but repairable. The crew chief looked at the cracked headers and offered his assessment of what had occurred. Doc recorded it in his notes verbatim. "I think the car is trying to tell us something." The car was, in fact, demonstrating a problem that Doc's traction model had accounted for in principle and misweighted in practice. Weight transfer under acceleration was moving mass rearward in a non-linear fashion, overloading the rear tires beyond their grip threshold before the theoretical power-to-traction ratio suggested it should. The front axle was lifting at the moment of maximum torque, reducing the driven contact patches from 6 tires to 4 at precisely the instant when you most needed all 6. The engineering advantage of 3 driven axles was being partially negated by the aerodynamics of a nose that wanted to point at the sky. Doc spent 3 months on the weight distribution, adding ballast forward of the front axle, modifying the front suspension geometry to generate aerodynamic downforce at low speed, borrowing techniques from high-lift aircraft stability work that he had encountered professionally. The revised car was heavier, slower in theory, and faster in practice. The Irwindale Raceway sessions of April 1967, 2 evenings arranged through connections and a cash transaction the details of which remain undocumented, represent the apex and the end of the project. By this point, Doc had made 17 modifications to the synchronization system, rebuilt 3 of the 6 engines after discovering their individual power outputs had diverged by as much as 12% due to differential belt wear, and developed a new launch procedure that deliberately staged the engines in two groups. Front 2 first, rear 4, a calculated fraction of a second later, creating a progressive torque curve rather than the instantaneous full power application that had been causing the front-end rotation problem. Run number 23, conducted at approximately 9:40 p.m. on the first evening under borrowed construction lighting, was the first complete quarter-mile pass the car made under controlled conditions. Two independent mechanical timing systems, carefully calibrated against a known standard, agreed on the elapsed time: 5.47 seconds. Trap speed: 247 miles per hour. In April of 1967, the NHRA top fuel elapsed time record was 6.34 seconds. Don Garlitz, the acknowledged master of the class, was running low sixes on his best days. The fastest human beings on a quarter-mile strip were running 6.3 seconds. The six-engine Dragster had just run 5.47. Run 25 produced 5.39 seconds, the fastest pass the car ever made, and the number that would be attached to the project in every subsequent account by the people who were there. Run 26 ended the project. The number 4 engine shed two supercharger impeller vans at approximately 16,000 revolutions per minute. Both vanes exited the engine bay at velocities sufficient to sever two fuel lines. The fire that followed destroyed the car from the front engine bank rearward in under 4 minutes. Doc was unharmed. The pressure suit and the aircraft-grade cockpit did exactly what they were designed to do. The car, which had consumed 4 years of engineering and more than $400,000 was not repairable. Doc collected the timing slips and the telemetry data from the aerospace recording equipment, loaded them into his truck, and drove back to the San Fernando Valley. He never built another racing car. The NHRA had never officially acknowledged the six-engine Dragster's existence. It had never sanctioned a run, never inspected the car, never issued a ruling on its legality. In 1968, it modified its top fuel class rules to require that all competing vehicles use a single engine and a single-driven rear axle. This was a significant institutional gesture. The NHRA does not generally rewrite regulations in response to cars that do not exist. It rewrote them in response to what the six-engine project had demonstrated was achievable, and more specifically, in response to the failure mode at Irwindale, which had been milliseconds and a few inches of fuel line from being fatal. The technical committee's concern was not simply the elapsed times, though those numbers were alarming enough. It was the failure signature. A six-engine car had failure modes that were categorically more dangerous than anything the NHRA's existing safety framework was designed to manage. If the concept were replicated by teams with less engineering rigor than Doc's group had applied, the results would be lethal. The institutional calculation was straightforward. Ban the category before someone less careful tries it. There was also, though it was never stated in any official document, the economic argument. A car running in the high fives in 1967 would have immediately rendered every other top fuel operation in the country non-competitive. The commercial structure of professional drag racing depended on something resembling a field. Events with multiple competitive entries, sponsors with multiple teams to support, promoters with meaningful races to sell tickets to. A single machine capable of destroying that field by running 0.8 of a second faster than the competition would not have been good for the sport as a commercial enterprise, regardless of its sporting legitimacy. Speed is not always rewarded in direct proportion to achievement. Sometimes the rulebook closes the door before the achievement can accumulate consequences. 3 of the 6 engines came through the Irwindale fire. 2 are in private collections in Southern California, in continuous private ownership since Doc sold them in 1969 to fund a house purchase. The third was donated to a technical museum, in the mid-1980s under terms requiring it not be publicly attributed to the six-engine project. Terms honored for 4 decades. The chassis was cut for scrap aluminum in 1968. The synchronization gear train, the project's most original engineering contribution, was disassembled and its components distributed among the 4 partners. The pieces are presumably in storage units and garages somewhere in the Los Angeles basin, unrecognized for what they are. The timing slips from Irwindale exist in private hands. They have been examined by 2 individuals with appropriate technical background in the 1990s. Neither materially disputed the elapsed time figures after examining the actual documents, rather than simply the claim. The telemetry data is more complicated. Recorded on magnetic tape using aerospace data acquisition equipment specific to a classified contractor's test instrumentation, it requires playback hardware that is essentially unobtainable. The tapes exist. The ability to read them may not. Doc retired from aerospace engineering in 1981. He gave one interview to a small drag racing magazine in 1973 and corrected the published account in 2 subsequent letters. He died in 1994. His engineering notes, reportedly several hundred pages of calculations, specifications, and test logs, passed to a family member who has not made them available publicly. The 5.39 elapsed time from Irwindale, if accepted at face value, would not have been equaled in official NHRA competition until the late 1970s. It would not have been clearly surpassed until the 1980s, when fuel management systems, tire compounds, and chassis engineering had each made independent advances sufficient to approach and then exceed what 6 engines and an aerospace budget had achieved in the dark at a Southern California drag strip. Drag racing history is, more than most motorsport histories, the history of ideas that were banned before they could be fully explored. The NHRA rulebook in any given year is partly a record of what competitors have tried and partly a list of what they are no longer permitted to try. The 6-engine dragster occupies a specific position in that history. It was prohibited not by name but by the category it represented. Banned before it could become a class, before it could attract competition, before the engineering logic it embodied could be tested against itself. The question of whether the ban was correct does not have a clean answer. The fire at Irwindale was evidence enough that even a carefully engineered version of this machine was operating at the edge of what containment systems and human reflexes could manage. A less careful version, built by a team without Doc's thermodynamics background and aerospace materials access, would almost certainly have killed someone before the safety engineering had time to develop in response to the power levels. The NHRA's caution was not unreasonable. What was lost alongside the danger was a decade of elapsed time progress. The 5.39-second pass that Doc recorded at Irwindale represented, in competitive terms, a 10-year leap beyond what the rest of the sport was capable of in 1967. The engineering path that produced it, multiple-driven axles, progressive torque staging, aerospace materials in a racing chassis, was closed off before it could be refined, before competitors could respond to it, before the technology could be stress-tested by the iterative competitive process that normally drives motorsport advancement. 6 engines, 3 driven axles, 18,000 horsepower, and 2 evenings in April. The timing slips say 5.39 seconds. The record books say nothing. Both of those things are true simultaneously, and the space between them is where the most interesting drag racing history has always lived. In the machines that ran too fast for anyone to officially believe them, and were banned too quickly for anyone to prove them wrong.